Okay, it's Saturday afternoon. Got some good results. Did a lot of good thinking. Was up, trying to get to sleep. Thought about what I was seeing yesterday with the data anomalies and tried some things. I did some definitive experiments about the accuracy. So when we left off yesterday, here's a graph of the error. Here's I had the radio in TCXO. I was measuring the GPS at two different frequencies relative to itself, and I had these plateaus that occurred very regularly. And if you look at even this data, this is the TCO at 200 and 900 hertz. I had these plateaus that seem to last the exact same amount of time, and it's weird that I would get if the 700 and the 200 are related to the same clock inside the my oscillator, why would they vary like this? One went up, one went down, and it caused a big shift in the hertz. Very, very strange. And here's another view of the same thing. And if you look, this is hertz on this side, I would get an offset of 15 millihertz. Here it's 45 millihertz, and it would last about 30 seconds. Very, very interesting. And this is with the cleaned up oscillator circuit. And well, what I figured out was that the program I use, FLDigi, it has an averaging function, and so I turned that off and I ran the same experiment. This isn't the same data as this, but it's the same experiment where I have the TCO, I had the GPS giving me a signal at 200 and 900 hertz, no averaging. And what you'll notice is that there's these occasional, here's a -1 hertz deviation in one of the measurements. And if you think about that, if I deviate by 1 hertz and I'm averaging that over 30 seconds, this 1 hertz deviation, if it's a sliding window, will perturb this entire signal, a 30th of that, or about 30 millihertz, which is sort of, a typical value that you see here. What you also notice is if I look here, these values of these deviations or differences are averaged, so I'm maybe at 0.005 hertz right here. If I turn off the averaging here, I'm at 0.06. So there's a lot more deviation when the averaging is turned off. So here it's 0.06, and then here the average is 0.006. So it's a factor of 10 at least by having the averaging on. But by turning the averaging off, I avoid the spurious signals causing long-term deviations in the frequency measurement. And of course, I can always average it myself. So and so this is a close-up of this part of the plot with the TCXO. And here I'm averaging the first 500 samples, and I'm at plus and minus 30 millihertz, which is a lot, but you can average this. And the noise that's causing this, it's power supply noise. It's Gaussian in nature, so you can usually average it out. There might be some trending noise or offsets that are happening, but most of this is just Gaussian noise. So doing that, and what we talked about with fooling myself by measuring my clock versus my clock, I decided to do a more definitive experiment. And so what I did is I took, I have a GPS unit which can do frequency synthesis, and it's called the Baudnar, and I set that to produce 10.0005 megahertz, and I set my GPO at 10.0002, and I set the radio at at 9.999800 megahertz. And what this will do is give me a nominal, the delta here is 400, so the GPS will appear to be a 400 megahertz signal, and the Bodnar will appear to be a 700 megahertz signal. And of course, since the TCXO inside the radio has a 12.6 hertz offset, it's actually going to appear at 412 and 712. And I had the GPS going, and it was going better than one slip every 200 seconds. So it was really spot on. And so I had these two signals going into the radio, and what FLDigi does, and this is the result, and that if you look, my offsets of the Bodnar, which is GPS, and my GPS was between 5 millihertz and 15 millihertz. So plus and minus, sorry, not plus and minus, but 20 millihertz total. That was my just differences I was measuring, and of course you can average those out, and you can see some things that look like large scale deviations. And here it looks like there was some temperature drift in either the Bodnar or mine. The Bodnar was sitting by a window, maybe the sun came out, but again, very, very well behaved. And so what FLDigi gives you, and of course these numbers all look kind of goofy, is basically the way it works is it gives you a spectrogram, like I've shown before, and you give it sort of a frequency window to look at, and it records deviations from those. And so for the Bodnar, I said it's around 712.6, and it was measuring deviations from that, and it tracks that. The transceiver has a setting, a place where you can set what the transceiver frequency is, because FLDigi does not know. It only measures analogs, audio signals. And so the transceiver frequency is combined with what the expected value is minus the measured error, and it gives you what it estimates the frequency as being. And the same thing for the GPS. And of course, reference and unknown, I got reversed. That's why I'm labeling up here. And so for the GPS, I said, expect it to be around 412.6, and it was measuring some deviations, and so it calculated what the estimated frequency was. What I did was, so these are the two frequency measurements, and I subtracted those two from each other, and I have this other column where I get what the frequency delta is. So if I was doing this for real, I don't know what this is exactly, but I can see it in the spectrogram display, and so I can say, centered on here, because I see the peak, and just record whatever it is. And I can subtract out my GPS, and I can get what the difference is. And then the diff here that I report is actually the measured frequency difference from the expected, because I know it's 300, and so I can get what this error is. And in the real test, I don't know what this is. I only know what the difference between the measured values is. I don't know what the difference is between the expected. But this is just for me in my analysis. So what you can do is, what I did is I averaged this error, or sorry, the difference between the frequencies over the first 300 samples. That's where it's kind of well behaved, maybe, before it goes into this, until it increases over here. And it was typically between, very, very close, around 300, like you would expect. And so this value requires no knowledge of what the frequency is, other than kind of knowing the ballpark value from the spectrograph. And so when I do that, I calculate the actual frequency delta as 5 millihertz away from 300, which is what the actual difference is. And so here in this value, I've calculated what the frequency delta is as 4.38 millihertz, again using this first 300 samples. So I have a write-up here where I sort of go through what I just discussed there. And it turns out that at 10 megahertz, if I'm at a plus 200 second slip time, the 10 megahertz reference is really 10 megahertz 0.005. And so actually, my assumption for what the GPS was is actually 5 millihertz higher, which means that the frequency delta here, having it be 5 millihertz lower, that's because it was 5 millihertz higher here. So if I add that back in, I get, an estimate of 30.0006175. And that's knowing how accurate my GPS is by knowing what the cycle slip time is. So if you do that, I'm again within this 500 microhertz absolute error that I calculated when I was measuring the GPS versus my GPS. But if you ignore that, I can set how accurately I set my GPS, I'm still 4 millihertz away from the true value, which meets my objective of being 10 millihertz away by a factor of 2. Now, of course, if I badly tune my GPS and I don't let it stabilize, its actual frequency will move around, then my calculation will be off. That's why I always paid attention, in the LCD to make sure that I was, over 100 seconds between cycle slips to make sure that my clock was really, really accurate. And it makes sense. If I'm running fast, then the difference between the GPS and the Bodnar will be less, and it's less by the factor that the slip rate tells you it should be. So it makes sense. Good math, good science. These are two completely asynchronous clocks that I'm measuring, my GPS and the Bodnar. They're both synchronized to a GPS signal, probably the exact same satellites, but they're two completely different oscillators, power supplies, frequency generators, what have you, and I still got exceptionally close, like I wanted to. The real frequency measurement test will be impacted by atmospheric noise, Doppler shift, uncertainty in the equipment on that side. There are a lot of things that will completely mess up the fact that intrinsically I can measure, 500 microhertz, and, best case with not knowing my frequency measurements, I can get within 5 millihertz. The Doppler and the noise in the atmosphere is easily an order of magnitude above that. So the only way you can, in the frequency measurement test, to get within 10 millihertz is to actually measure what the Doppler is at the time of the test, and then again take that into consideration. So there's lots of stuff going on. Really happy with the results. Kind of proves that the science and the engineering works. And the next step is to get the GUI going on the oscillator, so I can actually set the frequency without having to constantly reprogram it, and then also to have the auto tuning capability in there, so then I don't have to pay attention and constantly tweak the values up and down as it's running. But this is all good results. It's just what I expected. This is the ultimate, pure debug the equipment test, because it's two asynchronous clocks in the same room with not the uncertainties of the radio in there. So I'm gonna need to take a break. I've been cranking on this basically all day for the last 5 days at least, just doing measurements and trying to get things going, but it feels really, really good to have these results. It, at the same time works as expected, but it's also good to know that, the science and the engineering was correct and there wasn't anything unexpected like excessive power supply noise ruining everything. But this is a good result. I'm very, very happy with it. Cause for celebration. So maybe next week I'll have an update where I have some GUI and some control stuff going on. That's all software, so it's not necessarily as much fun as the hardware. Anyway, thanks for watching.